everyone, welcome back to the channel. So continuing in this series, in this video lecture we'll be implementing the topological sort ordering using breadth first search algorithm, or it is also called Kahn's algorithm. In the previous video we have already discussed how to write the topological sort for a given directed acyclic graph using depth first search strategy. So this is the second approach to solve the same problem. So here we are given the directed acyclic graph which has 6 vertices numbered from 0 to 5, and we want to find the topological sort for this graph. So let's recap the definition of topological sorting. So a topological sort is basically the linear ordering of these vertices such that for any vertex u and v, if there is an edge from u to v, then u must come before v in that ordering. Any such ordering where this condition is satisfied can be termed as topological sorting order, topological sorted order. So this is one of the examples 542310, which is a topological sort for this directed acyclic graph. Now you can see, you can observe any pair of vertices, let's say 2 and 3. We can see there is a edge from 2 to 3, and let's say 2 and 1, so we have to move from 2 to 3, then from 3 to 1 to reach this 1. So 2 comes before 1 in the ordering. Okay, now the topological sorting order is not unique. There can be multiple toposort orders for any directed acyclic graphs that we have learned in the previous video lecture. So let's see how we can use breadth first search strategy to solve the same problem. Now observe this topological sorting order. At the very beginning of the ordering we have two vertices 5 and 4. Why these vertices are present at the beginning of the order? Because observe that the in degree for node number 5 and node number 4 is 0. We have 0 in degree for this node and 0 in degree for this node. That means there is no preceding node from which we have to come to node number 5 or to node number 4. There is no parent node of node number 5 and node number 4. Hence they are the beginning nodes. We can begin from these nodes. We can either begin from 4 or from 5. So any ordering like this, ordering like 4 5 2 3 1 0 is also valid. This is also valid. Okay, now from node number 5 we can move to node number 2. That means 2 must come before node number 5, and hence we are writing 2 here. Then following the directed edges we will move to node number 3. So 3 must exist after node number 2, so we put 3 here. Then from node number 3 we move to node number 1, so 1 must exist after node number 3, 2 and 5, so we put 1 right here. And there is no out degree for node number 1. We can't move to any other node from node number 1. So we pick another node which has in degree 0, that is node number 4. From node number 4 we can move to node number 0. So we put node number 0 here. So what is the observation here? We are picking up the nodes which has in degree as 0, and we are just following the directed edges which are leading us to the final vertex with out degree as 0. Okay, that means at the very beginning of the ordering, any topological ordering, we must put those nodes which have in degree as 0. Fine. So the very first step to solve this problem is to find the in degree of the nodes, is to find the in degree for all the nodes. Okay, so how would I find the in degree? We'll see how we can do that, but we somehow process the in degrees for all of these nodes into some array, and we are calling that array as in degree array. So in degree is basically nothing but the number of incoming edges towards a node. For instance, for node number 5 there is no edge incoming, so in degree is 0. For node number 4 the in degree is 0. For node number 1 we have 2 incoming edges, hence the in degree is 2. For node number 0 in degree is 2. For node number 1 in degree is 1. For node number 3 in degree is 1. Okay, now the next question arises, can there be any directed acyclic graph which has in degree as, like, which do not have any node with in degree 0? No, we can't have a directed acyclic graph which do not have any node with in degree 0, with in degree like not equal to 0. We must have at least one node in a directed acyclic graph which has in degree as 0. So mark this note point that for any directed acyclic graph we must have one node at least which has in degree 0, and we must have one node at least which have out degree 0. So what is out degree? Out degree is basically the number of edges which are emanating or going out from any node. For instance, for this node number 5 we have two edges going out of this node, this edge towards node number 2 and this edge towards node number 0. So we have out degree as 2. For node number 4 we have out degree as 2. For node number 1 the out degree is 0. For node number 0 the out degree is 0. For node number 3 the out degree is 1. For node number 1 for node number 2 the out degree is 1. Okay, so for any DAG we must have this condition. We must have at least one vertex or node with in degree 0, and we must have at least one vertex with out degree as 0. So what is the proof of this fact? So imagine in any directed acyclic graph, S represents the longest path which we can get. So starting from any node we can get the longest path in a directed acyclic graph. That has to be this path as S. So that means there has to be a starting vertex, let's say node number 5. The starting vertex must be the one which has in degree as 0, because if it has in degree non-zero, then that means, let's say we have some node here, then that means the longest path must not start from 5 but it must start from this node. Okay, and in the same way this must end on a node, the longest path must end on a node which has out degree as 0. For instance, let's say it ends on node number 3. Let's say the longest path ends on node number 3, but we can extend the path by moving one more edge towards 1. Now that would be even longer, hence the path which we are assuming is not the longest path. That means for the path to be the longest, the starting vertex must have in degree as 0 and the ending vertex must have out degree as 0. Only in that case there is a longest path. So for this graph the longest path would be this, starting from node number 5 going to node number 2, 3 and finally ending at node number 1, which has 3 edges and 4 nodes. This is the longest path. Okay, now if there is no cycle then there has to be a longest path, because if there is a cycle then we can't have a concept of longest path as well, because we can just keep moving in a cycle and the path will keep on increasing. Okay, now I hope this is clear at this point. Let's see how we can solve this problem, how we can apply breadth first strategy, how we can arrive at the BFS strategy, starting like knowing the ideas we have explained till now. So what we're going to do is we just want to start from node number 5 and node number 4. So since we processed node number 5 first, then we processed node number 4 first, they had in degree as 0. So let's say we take a queue, we put them in a queue, because we processed node number 5 first. So we push node number 5 first, then we push node number 4 because they had in degrees as 0. So we just pop node number 5 and we process its adjacent nodes. So we move to node number 2 and so we pop node number 5 and we take another array that will store the answer, and we will push node number 5 at the beginning of that array, or top of sort array. Now we are processing node number 5 at this point, which has in degree as 0. So from node number 5 I would apply, since I am using breadth first search, I would move to its adjacent nodes. So I would move to node number 2. It is unvisited, so I will move to node number 2. It has in degree as 1. So whenever I am moving to the adjacent nodes, so the strategy is simple, just move to the adjacent node and remove the edge and try to make the in degree as 0. It has in degree as 1. After I remove this edge, the in degree will become 0. Now, whenever the in degree of any node becomes 0, we can always push that node into the queue for the processing. So the in degree for node number 2 becomes 0 and we push it into the queue. Okay. Then we process this node, that is node number 0, because it is also the adjacent node of node number 5. So we move to node number 0, its in degree becomes 1. It doesn't become 0. We still have one incoming edge towards node number 0. So we can't push it into the queue. Okay, so we just remove node number 5 from the queue and we push it into our answer array. And we remove these two edges. So let's just unmark these edges here. We don't have these edges at this point. Then we will process this node number 4. We pop this node number 4, which is this one, and we move to its adjacent nodes. One of the adjacent nodes would be node number 0, and we simply remove this edge. We remove this edge and the in degree will become 0. Now the in degree for node number 0 becomes 0, so we push this node into the queue. And we'll do the same for node number 1. We traverse this edge, and the in degree becomes 1. So it doesn't go 0, hence we can't push node number 1 into the queue. So these two edges are removed. So since we popped out node number 4, we'll push this node into the answer array. Now we'll pop node number 2 from the queue. We'll pop node number 2, this one, and we simply visit it. Okay. And we basically traverse the adjacent nodes of node number 2, that would be node number 3, and we'll make its in degree to be 0 by removing this edge. So we remove this edge and the in degree for node number 3 becomes 0, hence we push this node into the queue. And we basically push the node number 2 into our answer array. Okay, now this edge is removed. We have removed this edge. Now we'll process this node number 0, this one, and we can see that there is no vertex, there is no adjacent node for node number 0. So we just push it into our answer array. Okay. Now we'll process this node number 3. We'll process this node number 3 and we basically move to node number 1, which is the adjacent node of node number 3. So this node has in degree as 1. It will become 0 after I remove this edge. And I push the node number 3 into the answer array, and I push this node number 1 into the queue because its in degree has become 0. So this edge is again removed. This edge is removed. Okay, now we process this node number 1. We pop it out of the queue, we push it into the answer array, and then we process it. We just traverse it. We mark it as visited. Now all of our nodes are visited and we have a ordering here in this array. This ordering is basically nothing but topological sort. So that's how we process it. Fine. So you got the idea how we are doing it. All we just did is take a queue, start from the all we just did is we have a directed acyclic graph. We computed the in degree array for that graph, which basically stores the in degree for every node of the graph. We took a queue, we pushed those nodes which had in degrees as 0, and then we start the BFS by processing only those nodes which has in degrees as 0. And as we eventually traverse the adjacent nodes, we basically decrease their in degrees by removing the edges which are leading us to those nodes. And whenever the in degree of the adjacent nodes becomes 0, we push those nodes into the queue. And whenever we pop a new node from the queue, we got to push that node into the toposort array. So in this fashion, we'll have our answer stored in this toposort array, and we return this answer right at the end of the function. Fine. So let's jump to the implementation part. First of all, let's see how we can find the in degree for each node. So this is our directed acyclic graph. This is the corresponding adjacency list for this graph. So basically for every node we have a vector, the array of those nodes which are connected to this node here. That means from node number 5 we have two outgoing edges towards node number 2 and node number 0. So for node number 5 we have two edges, which one goes towards node number 2, which is this one, and another goes towards node number 0, which is this one. That's for this adjacency list stores. Okay, so how we can find the in degree for every node? We just start traversing every node starting from node number 0 till node number n minus 1. So here n minus 1 would be 5 because we have 6 nodes. So we can see that 0, 1 had in degrees as has out degrees as 0. Okay, and let's process the in degree array. So we start from node number 0, we traverse the adjacency list corresponding to that node. We can see that we have empty array for node number 0. That means there is no edge which is outgoing from node number 0. Then we move to node number 1. We can see that we again have an empty vector for this node. Okay, that means there is no edge which is going out from this node. Then we move to node number 2. We can see that the corresponding vector for node number 2 contains node number 3. That means there is an edge from node number 2 to node number 3. So we traverse this node number 3 and we increment the position the corresponding value for node number 3 by 1. So this is my in degree array. This is my in degree array. In degree array, initially all of these values are 0. So for node number, so we have already traversed node number 0, 1 and 2. For node number 2 we are moving to node number 3. That means the in degree of node number 3 will increase by 1, so it will become 1. Then we'll traverse this node, that is the adjacent node of node number 3, and we can see that we have node number 1, so in degree of node number 1 will increase by 1. Then we'll move to node number 4. We will traverse 0 and 1, so in degrees of 0s and 1 will increase by 1, so it will become 1, it will become 2. Then we'll traverse this node number 5. The in degrees for node number 2 and 0 will again increment by 1, so it will increment by 1, this will become 2, and this 4 and 5 will have 0, 0. They have in degrees as 0. Node number 0 and 1 has in degrees as 2. We can see that. So we basically push those nodes which has in degrees as 0. So we push node number 0, so we push node number 4 and node number 5 into the queue, and we start our BFS. Okay, so this is how I process the in degree array. Let's jump towards the final implementation of the algorithm. So this is the top sort function which takes in the number of nodes and the adjacency list into the array. Then we have my in degree array which will be resized to n and represents the number of nodes in the graph. Then we'll traverse the entire nodes from 0 to n minus 1. So for every node I will traverse its corresponding vector or the adjacency list. Like for in this case, for every node I will traverse this array, and for every element in that array I'm gonna increment the in degree by 1. That's what so this is just I'm just implementing the approach which I explained here. I'm calculating the in degree for these nodes. Then I will declare a queue which will be used to perform the BFS. So here I am just iterating over all the nodes, and for all the nodes which has in degree to be 0, I'm gonna push those nodes into this queue. Fine. Then here at this point I will have those nodes into the queue which has in degree to be 0. Then this is my answer array which will be used to store the top sort order. Then I will iterate over the queue. I will perform the BFS till the queue is not empty. I will pop the front element from the queue. Okay, here I am popping it out, and I will push that element into the answer array, and I will traverse the elements which are the neighbor elements or the adjacent nodes of the current node. That is just performing the usual BFS. And for all the neighbors which I am traversing, I am decrementing the in degree by 1. That is, I'm just removing that edge. I'm removing the edge from the current node to the neighbor node. Now, if after removing the edge at this point, if the in degree becomes 0 for that neighbor, then I'm gonna push that neighbor into the queue for further processing that neighbor. Okay. Now, in this fashion, when I have processed all the nodes, I'm gonna have my answer array prepared. That will store the top sort for this given directed acyclic graph, and I will return that answer right at the end of this function. Okay. So that's just all we have to do in this problem. Let's jump to the code implementation. So I will be implementing the solution using C++ language. Okay, so I would be implementing this function, toposort function, which takes in the number of nodes. So let's just say it returns a vector. Let's call this function to be toposort. It takes in the number of nodes n, and it takes in the adjacency list, which is going to store my directed acyclic graph. So here, first of all, I will declare an array. Let's call it in degree array, which will store the in degree for all the nodes. So I will iterate over all the nodes, starting from the node number 0 till node number n minus 1, and for every node I will traverse its neighbors. So I will traverse the neighbors of every node, and for those neighbors I'm incrementing the in degree by 1. Okay, so here I'm processing the so here I'm calculating the in degree. After calculating the in degree, let's declare an array, that is answer array, which will store the answer for the given node. Then I will store the queue, then I will declare a queue. After that I will iterate over all the nodes of this graph, and for every node I'm gonna see if the in degree is 0 or not. If it becomes 0, then I'm gonna push that node into the queue. Okay, then I will run the BFS, the usual BFS, till this queue is not empty. So this is QU, till this queue is not empty, and I will pop the current element from the queue, queue dot pop. Then I'm going to iterate over the neighbor nodes for this given adjacency list, and for all the neighbor nodes what I'm going to do is I will so since I'm popping this node out, I have to push it into the answer array. So I have to push it into the answer array, because this has n degree to be 0. So I will push this current node into the answer array. I will traverse its neighbors, and for every neighbor I will decrement the in degree to be in degree by 1 unit. So for this neighbor the in degree will be decremented by 1, and here I am checking if the in degree for that neighbor becomes 0. If it becomes 0, then that means I can push this node into the queue, push this neighbor node into the queue, and that's all. So after I end up running this loop, I will have my answer array prepared, which I will return from the end of this function. So in this fashion I will have my toposort function, and this is the implementation in C++ language. Simple BFS with a little modification. Now let's implement the same solution in Java. Let's implement the solution in Java language. Let's create a class. Let's call it a solution class. Let's create a function, call it static. It returns an integer array. Let's call it toposort function. It takes in the number, it takes in an integer n, and an array list representing the list, the graph itself. Let's call it adj Let's declare two arrays, topo array which will store the answer which has a size of n. Let's declare another array in degree which has a size of n. It will store the in degree for every node of the graph. Iterate over all the nodes of the graph starting from node number 0 till n minus 1. For every node, iterate over its neighbor. And it can be like adjacency get I. So I'm traversing the vector corresponding to node number I, and for every node I am going to increment the in degree for that node by 1. Okay, so this will prepare my in degree array. Now I will declare a queue. So let's declare a queue of integers. Let's call it QU new linked list of integers, and that's all. So this is my queue, and iterate over all the nodes of this graph starting from node number 0 till n minus 1. So if in degree for any node is 0, then push that node into this queue, add it into this queue. Now finally run the BFS algorithm till this queue is not empty, and just pick up the current node. Let's call it current, and it would be, I would say, q dot call and q dot pop. I'm gonna remove this node, and I have to declare an index. So and this will be used to store the index for any node. So I will store this current node into this topo array, topo int plus plus for this current node. Now iterate over the neighbor nodes of this current node. So for neighbor nodes, the in degree decreases by 1. Then iterate over the, if the in degree goes 0 for the neighbor node, and add this node into the list, into the queue. NEI. Okay, so in this fashion, just keep adding the nodes into the queue and keep processing it. I would have my topo array prepared at the end of this iteration, at the end of this while loop, and I will return that array, topo array, from here. Okay, so this is my implementation in Java language. Fine. So okay, so that's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel. So continue in this topological sorting series. We'll be solving a lot of, we'll be also solving a few problems related to this algorithm. So stay tuned with me. I hope to see you all in my next video.